Okay, hello everyone. So I'm finally back with making conlangs. So let's start, shall we? The first lesson of today, because before I can delve into the complexity of extreme lengths, I need to explain a bit some prerequisite that we need to then approach this language with a much more in-depth analysis. The one of the first thing to understand to comprehend extreme lengths are production rules. What are production rules? This by itself will be a topic that can be done in like a year or something. But for now, let's keep things simple. A production rule is our actually production rules are a set of rules that can be used to describe the formal grammar of a language. With formal grammar, we are not talking about grammar in natural languages, so verbs, tenses, noun cases, and stuff like that, but exactly the syntax of a language, how it is written, how the words combine together to create a final language, and a way to check whether words, actually when sentences are valid. Okay, so a so we have our grammar that has a set of rules. Each rule is composed like this. We have a left hand side, an arrow, and the right hand side. The left hand side is an identifier, okay, the name of the rule that we want. Then we have an arrow, and now we have the right hand side. So right hand side can be an ID, or we can have specific rules. For example, we can have one ID, another ID, and so on. We can concatenate multiples ID together. Another uh, another feature we can use on the right hand side is the OR. If we have an OR, the left side and the right side of the OR is an option. So for example, if we have a production rule with the rule A or B, it means this rule can either be rule A or rule B. Okay, so this vertical bar represent an OR. And we can chain this rule together, so we can do A or B and C. In this case we became rule A or rule B, C. uh, another another important rule is the optional, the question mark. So if we have rule arrow A B with a question mark, this question mark refers to this B and it means it's optional. Okay, so we can describe this rule as A or AB because B is optional. Okay, so if you see a question mark after an identifier, it means that we have that the previous identifier is optional. Another rule is the star, okay, the asterisk. This indicate 0 or more. For example, if we have rule arrow A, B star, this means that we can have A one time, B 0 or infinite amount of time. So A, B, B, B up to infinity. This will be a valid rule, okay? Because we need at least 0, so it's optional and infinite amount, okay? Depends on our grammar. Same thing goes for plus. Plus is 1 or more. So if we have rule A, B plus, it means that we can have at least A, sorry, we need to have one A and B at least once. So A, B is valid. A by itself is not. While star A is valid because B in this case is optional, okay? And then we have the brackets. Brackets represent a group. So for example, if we have rule A, B, C plus, this means that we need to have our rule has at least one A, no sorry, it has exactly one A, and then the sequence BC at least one time. So BC, BC, BC will be a valid rule in our grammar, okay? So remember these rules. We have identifier or, open parenthesis, plus, star, and question mark, okay? So now that we have a basic idea of how we can describe production rule, let's try to use them, okay? Let's create system that allows, actually a grammar that allows to okay, let's say that we have a language that can only describe an item and its color, okay? So a valid sentence will be the house is red, okay? So we can associate an item with a color. So let's create some placeholder, and this will be an object, and this will be a color, okay? So if we want to describe this grammar, we will say that a sentence is an object, the word is, followed by a color, okay? Now, what can be an object? An object can be, for example, house, or it can be dog, okay? And a color, what can be? Let's say it can be red or white, okay? And these are our production rules, okay? So let's considering this grammar, let's see if we can make a valid sentence or we can read it. So for example, let's start with initial symbol. Initial symbols, we need to replace the left hand side with the right hand side. So let's replace S with its rule. So remove S and replace with object is color, okay? Now let me draw this arrow. So from this we generated these three rules, and now we can keep going until we cannot expand any other rule. Object can be house or dog. Let's pick house for now. And the color can be either red or white. Let's pick red. Okay. What we drawn is a parsing tree. Okay. which is basically a tree, so a structure where we have parent and children, and it parses a sentence. So house is red. Okay, we read from left to right only on those symbols that are non-terminal. These rules are said to be non-terminals, okay, because they are not the end of the tree, while rules like these ones, these are terminals, okay. So if we read the terminals here, house is red, this is a valid sentence. We could have replaced with white, so house is white, okay. And this is a really simple way to describe a syntax. Let's try to do another example. The classic example that everyone explains, which is, let's say we want to make a language that can parse a sequence of parentheses, okay? So we can have any parentheses we want, empty brackets, and the same number of close parentheses before the opens, okay? So something like this will not be valid because this has no closer, while this is not valid because this has not opener, okay? So let's try to analyze this. The first case is simple, okay? When we have open or close. So let's say our initial symbol can be either open, actually let's say op is this symbol right here, okay? And then we have close, that is this symbol. So initial sentence, initial symbol can be either open or close, okay? Open followed by close. So let's so we have 1 2 3 4, 1 2 3 4. So let's remove these and replace with s, okay? So now we have 3 s start and 3 after it, okay? And see, we see another rule. So another rule, it could be open symbol close, okay? Let's replace this with our rule. We have open open close close. We see this rule is already covered by this case, so we don't need to add anything. Open close and so on. As you can see, we finally we create a grammar that can parse this exact sequence. As you can see, these two are identical except the S in the middle, so this is optional. So we have sentence open, sentence optional, closed, okay? And this is our production rules, okay? Why I explain this? I explain this because uh, these are used a lot when making extreme lengths, because these can describe features of the language, okay? For example, you can say that a noun can only be followed, a noun is a word followed by an optional suffix, okay? And you can say that a suffix could be could be a word followed by modifiers, at least 0 or more modifiers, okay? So if you have a noun here, let's replace with its left hand side, right hand side. Now let's say that we don't want this optional, so let's replace suffix with its word and modifier. Let's say that we have at least one modifier, and now we have our sentence. in this case are noun. Okay, so understanding this is really important because I will use this notation throughout the entire series. Okay, let's do more examples. Let's say we want to write a grammar that can parse a number, okay, a decimal number. So what is a decimal number? We have 1, 2, 10, 35, and so on, okay, and we have 0, okay. We don't want this sequence because this sequence can be just written as 1, okay. So we want to avoid this case right here, but this is a decision that we can make. So if you want to allow this, you can do it. For this example, let's ignore this and consider this case. So a number, we have a digit. Let's define a digit as numbers from 0 up to 9. Okay, so parentheses represent optional group, and these three dots represent from to. So you can imagine this as in our example, you can replace open parentheses, open square parentheses with open quotes, 0, close, open, 1, or, and so on. Okay, so 0 or 1 or 2 or 3 up to 9. Okay, so now we said that a number can be a sequence of digits. Okay, so at least one digit, because an empty number is not a number, so we need at least one. However, this would allow 0 to start, because if a number is a sequence of digits and a digit can be any number, a symbol from 0 to 9, this would be a valid number, which we don't want. So we introduce another rule. Let's say uh, let's say header can be only the digits from 1 to 9, excluding 0. Okay, so we rewrite our number to be header followed by digit, but this time 0 or more, because we already have 1 from here. Okay, however, this will not be able to describe the number 0, because if the header starts from 1 up to 9 and digit can be 0 up to 9 optional, we don't have a way to describe 0. So let's add a simple or rule. So instead of being just header digit, it could be header digit or 0. Okay, and we have done this section of the grammar. Okay, so it's really important that you understand this concept. You can do a lot of exercise on your own. Here is one that you can try. Describe the production rule for a grammar that allow you to describe the color of street light. Okay, so we have symbols red, green, and yellow, and you need to describe the color in this format. So street light was from color to color. Okay, so the street light was red, from red to green, red to yellow. Of course, you don't have to, you need to, the sequence is green, yellow, and red. So you cannot do from yellow to green because you are going backwards, and this is not allowed. Okay, so you need not only to describe this, to formalize this language, but you also need to check impossible case. Okay, so now I give you some seconds to pause the video before we go to the other topic. Okay, so now that we have actually no, yeah, uh, actually I put another, I will make another topic in the other video. So right now I need to explain one thing about production rules. Okay, so we said that we have a, when we use production rule, we generate a parsing tree. Okay, a parsing tree is a tree that has a parent, and parent can have n children. Okay, so we have children 1, children 2, up to whatever children. These children can either be leaf or another intermediary node. So if it's leaf, it doesn't have an end. If it's not a leaf, can have more children. Okay, so this is a tree. Okay, it goes from top, from parent, with a relationship from parent to children, and we can go until all the children are leaf nodes. Okay, so we can describe this tree into, for example, let's say that we have a tree like A that goes to B, C, B goes to A, D, and C goes to E. We have three type of visits. Okay, we have a pre-order, post-order, and in order. Pre-order is also called prefix, post-order is postfix, and in order is called infix. Okay, so infix, when you see the term infix notation, tree in infix notation, it means in order. Okay, so pre-order is a representation when we have a parent followed by each children. Post order, we have children followed by parent, and in order we have the left children, parent, and right children. For example, let's describe this tree in a pre-order notation. So pre-order means that the parent needs to be written before the children. So we start from the root of the tree A, and we need to write it because we need to write the parent first. Then we need to go to the children, and we need to treat these children as their own subtrees. Okay, so we need to write, starting from left, the next children because it's pre-order. We continue this tree, so A, D, and then we go back and we go to the next children, which is so let me remove, okay, which is A, B, A, D, and then C, and then E. Post order is the same, but the parents is written after its children. So we start from A, but we don't write A. We first write its children, so B, and then C, and then A. To write B, we need to write before the children's and then the parents. So we write the children A and D. Because these are leaf nodes, we can just write them. So A, D, then so we go down, we reach a leaf, we drop the leaf, we go to the other children, we draw the children, we go back to the parent, we go back to the parent, but then we go to C, then we go to E, we draw E, then we draw the parent, and then we draw the parent again. So A, B, A, D, so A, D, then we draw the parent, then we need to draw the children of A, so C, then the children of C, which is A, then we go to C, and then we go to A. Then in order, we draw the left children and the right children. So first we draw the left children of A, which is B. The left children of B is A. Then we need to draw the node, the parent node, the left children. Then we need to go back, draw the parent, children, left children, and parent. Because this does not have anything here. Okay? So let's see. A, B, C, A, D, A, B, D, A, B, D, A, E, C. Okay? So if we see A, B, C, okay? So, let me show you. Pre-order, we first need to write the parent followed by the children first. So parent, then we write the children. This is a subtree, so we write this one. Then we write the children of B, so A, D. Then we go back to A and write the children of A. Okay? Post order means that we first write the children of A, of the parent node, and then we need to write the parents. So we first write the children of A, which is B and C, and then we write A. Then we write the children of A, and so on. Basically, if you still are a bit confused about this, imagine this sequence. So we have a parent, and then children 1, children 2. So pre-order means that we write P followed by C1. Actually, let me do C3. P1, P, C1, C2, and C3. Post order means that we have post order means that we write first children 1, children 2, children 3, and then parent. And then we have in order, which is children 1, parent, children 2, and children 3. Okay? Okay, now that this topic is done, let me, I think we can close this. If you have any more question, you can ask me in the comment section. And if there are a lot more, I can, if there are just a handful of questions, I can answer them directly from the comments. Or if there are a lot of them, I can create a following video explaining this. So now another quick example, quick exercise to do is to write the pre-order, post-order, and in-order version of the three 1, 2, 3, 4, 5, 6, 7. Okay, so try to write these three in the pre-order, post-order, and in order format. Okay. Thank you for these quick lessons about production rules and parsing trees, and see you in the next one.